Right, I'm going to try and go through some content which, if you have very limited time, you can review, and hopefully these questions come up in the real exam. So to start off with, looking at rates of reaction. Now, rates of reaction is quite a good topic to make sure that you review. It comes up every year. The main thing to start off with is looking at the different experiments that you do. Now, there's three main experiments. You can collect a gas where the reaction produces a gas, and you can collect it using a measuring cylinder or a measuring syringe or a gas syringe, and you can then work out the rate of reaction from that. So that only works if the reaction obviously produces a gas. The second experiment that you would do is using the same reaction where there is a gas produced, but now what you're going to be looking at is mass loss. So you do this where you take a balance and you carry out the reaction on top of the balance, and you lose mass, or the reaction loses masses, and then you measure the rate of reaction. And then the other one is where you take out the disappearing cross. So it's a precipitation reaction, yeah. So this only works again if a reaction produces a solid. If the reaction doesn't produce a solid, then you won't be able to carry this reaction out. Now, the main thing that you need to remember from this is you'll often get a graph, and the graph goes off like this, and then it levels off. So from there, what you need to be able to do is work out the rate of reaction. The way you work out the rate of reaction is you take the tangent of the graph at a particular point. So say you're taking the tangent at this point here, and then you compare that with working out the rate at this point, where again you take a tangent, say at this point, and you do exactly the same as you would in maths. You take the gradient of the graph. The gradient basically tells you the speed of the reaction, and to work out the gradient you do up divided by cross, rise over run, and then that gives you the rate of reaction at that particular point. And what you can see is that the rate of reaction is fastest at the start of the reaction and starts to slow down as the reaction proceeds. So that's what you would need to be able to do for the first part of rate of reaction. Now, it then moves on to looking at those four different variables that can affect the speed of a reaction. So those are the variables: temperature, pressure or concentration, catalyst, and surface area. Now, with these variables, what you need to make sure you do is you talk about frequency of successful collisions. So you need to consider that and talk about the frequency of successful collision. Right, just a few other things on some last minute revision. So if we're talking about equilibria, remember when we're talking about changing temperature, the main thing to think about is which reaction is endothermic and which reaction is exothermic. So if you increase temp, then the equilibrium will shift. So equilibrium will shift to, so if you increase temperature, equilibrium will shift to the endothermic direction. It's important to say direction, not side. It's the side that is endothermic. So say you've got A plus B gives you C plus D, and that is your endothermic. Then if you increase temperature, you will have more of the forward reaction, which is the endothermic reaction happening. And obviously if you decrease temperature, then the reverse happens. If you decrease temperature, equilibrium will shift to the exothermic direction. So in this case, more of the reverse reaction will happen. So once you know one of them, you can then easily learn the other. So temperature is to do with endothermic and exothermic reaction, and pressure. So if you're talking about pressure, the main thing to think about is the number of moles on either side. So on this side you've got 3 moles of gases, on this side you've got 4 moles of gases. So if you increase pressure, equilibrium will move to the side which reduces pressure. So the one that reduces pressure is the reverse reaction, so then there will be more of the reverse reaction. So increasing pressure, equilibrium will shift to the side that produces less moles of gases. So in this case it's the reverse reaction. You can even say it will produce more A and B, so that means it's going to happen in the reverse direction. So that's pressure. And then the other one is concentration. Now with concentration, the main thing is if you've got A plus B produces C, so you want lots of C. So if you want lots of C, you increase the concentration of A and B continuously, then the equilibrium will shift to produce more C to try and reduce the amount of A and B. And if you then have at the same time a constant removal of C, equilibrium will try and shift to the right to make more C. So that's why equilibrium in both cases will move to the right, because you want to make lots of C. So concentration is just about A and B continuously going in and C continuously coming out, and that will increase the concentration of C. And the last one is a catalyst. Now the catalyst, we know that speeds up the rate of reaction, so it speeds up both reactions. So it doesn't have an effect on equilibrium position, but it just increases both forward and the reverse reaction. So that's why it has no effect on the position of equilibrium. Right, the last bit on equilibria is just a couple of things on dynamic equilibrium. Remember, dynamic equilibrium, you need to have a reversible reaction. It needs to be in a closed system, and the rate of forward reaction equals rate of reverse reaction. So that is basically your few factors that you need to make a dynamic equilibrium, or make a reaction at dynamic equilibrium. Right, let's quickly move on to looking at crude oil. Remember, crude oil is a mixture of hydrocarbons. Now, what is hydrocarbons? Hydrocarbons are compounds that contain hydrogen and carbon only. You've got to use the word only, otherwise you won't get that second mark. Saturated, single bonds only between carbon-carbon. Unsaturated is carbon-carbon double bond. Carbon-carbon double bond. Now I'm obviously going through it quickly because the idea is to try and get any extra marks that you can as a last minute revision. Then you need to think about alkanes and alkenes and cracking. Remember, alkanes, you've got methane, ethane, C2H6, C3H8, propane, and C4H10. butane, and the general reaction, general equation for that is CnH2n plus 2. So these are alkanes. Right, I'm going to quickly go through crude oil and fractional distillation. I won't necessarily write it all down. Remember, fractional distillation, usually it's something like this, where you've got different fractions coming off. What happens here is crude oil is vaporized, it goes in here. What you've got is cool temperature there, high temperature there, so there's a concentration gradient, and as the crude oil, which is a gas, is vaporized and goes in, it starts to move up, and as it moves up it starts to condense at different temperatures, and then it will then liquefy, and then it will come off at different fractions depending on which temperature it condenses. The short hydrocarbon chains are at the top, the long hydrocarbon chain are at the bottom. Bitumen tends to be one of the longer hydrocarbon chain used in road tarmacs and road surfacing, and then you've got propane, which is one of the small short hydrocarbon chain often used in camping canisters, because it burns really easily, and then a few things in between. So that is your fractional distillation of crude oil. Thermal decomposition is cracking. The reason why we need to crack stuff is because the demand for short hydrocarbon chain is much greater than the supply, and therefore you can take a long hydrocarbon chain and you can crack it into small bits. It is you need a catalyst, and you need high temperature around 500 degrees Celsius. That's the catalytic cracking, and that will give you two products. Usually it will give you a alkane and an alkene. So when you take a hydrocarbon chain, say C10 H22, you crack it. Now the way to do it is you'll obviously get two products. What you do is you look at what you have, and you then work out the difference between the two. So say this is C8 H18, the difference between the two is C2H4. That's an alkane, and that's an alkene. And then these alkenes can then be used to make polymers. So you can make polyethene from this alkene, which is ethene, and polyethylene, an example of that is basically plastics, or lots of variations of plastics that you can use for a number of different reasons.